I want to thank everybody again for coming. This is a great attendance. It's been for all 4 of our spring lectures. This is our last one. Everybody keeps asking me for a while. I was going to bring something. What I did want to tell people was if you want, we do other events throughout the year, even though we only do our lecture series in the spring. We probably will be doing some events over the summer, and we have an open house at Carnegie in October. And if you are not on our mailing list, you should make sure before you leave you sign up on our mailing list. It's upstairs. If you get the brochures for the lecture series in the mail, then you're on our mailing list. If you didn't get that brochure, then you're not. So please, it's pretty simple. So please, we encourage you to sign up because we would hate to see you miss some of those other great events. And we thank you all for coming. It's been really great. Let's see what other things we're going to say. So normally, you're probably all familiar with most of our speakers actually come from Carnegie. But every year we try to feature one outside astronomer. And we pick those astronomers from some of our partner institutions. This year we picked Bob Kirshner from Harvard. Harvard is a great partner for Carnegie. They are involved in both our Magellan Telescopes, which you'll remember I talked a little bit about in our talk for those of you who were there, and the giant Magellan Telescope, the next generation telescope that we're building. And so we're very excited to have this partnership with Harvard. And we're really excited to have one of their finest professors, Bob Kirshner, who many of you will know. Bob is famous for his work on supernova, and particularly for observational cosmology. And I think most of you will know, all year long people keep asking me about, all spring they keep asking me about dark energy, and I keep saying, just come to Bob Kirshner's talk, and he will answer every question you have about dark energy. Don't ask me. Bob was part of the team that actually, one of the 2 teams that really discovered the fact that the universe is not only expanding, but accelerating. And this is, of course, what has led to the notion of the dark energy. And I would argue, I think it's actually not much of an argument, in fact, to make, that this is the biggest result in observational cosmology since Carnegie astronomer Edwin Hubble discovered the expanding universe the first time. So this is a really beautiful result, and one I think that shocked all of us in astronomy. And you're going to hear about that tonight. And Bob has been rewarded for his amazing work with many, many prizes. Most recently, in the last few years, the Gruber Prize, which he shared with this High Z Supernova team, and the Breakthrough Prize, which was just awarded in December, I think, of 2014. I mean, it's really remarkable. And even more remarkable, 2 of his students got the Nobel Prize, which is really in physics. I mean, he really... I mean, it's really a great accomplishment for an astronomer. So we're really happy to have him here. One other thing I wanted to say, and this I have to pull out my notes because I don't remember the name of it exactly, but he has an amazing popular book, The Extravagant Universe, and something.
Oh, there'll be a slide.
Oh, there's going to be a slide. He's a great salesman. So what I would tell you is that I would encourage you, if you want to know more about the story of dark energy, you will, after this lecture, I would really encourage you to check out Bob Kirshner's book. So let's welcome Bob to the stage.
Thank you, John. Thank you. I've got to say, that was a terrific opening act, and I'm not talking about John. I'm really excited to be here and back in Pasadena again. So what I want to talk about tonight in about 40 minutes is 14 billion years of cosmic history. To do that, you have to leave out a lot of details. And so what I usually do is leave out references to the work of others. And that seems to boil things right down. So I show you in this first slide back here a beautiful photograph of the Magellan Telescopes, Carnegie's Magellan Telescopes, our Magellan Telescopes, in Chile. And you can see the arching band of the Milky Way that is so conspicuous in the dark southern skies. It's interesting to think that 100 years ago, scientists did not yet know that our Milky Way was just part of the universe. At the time, in 1915, when Einstein was inventing his theory of general relativity, which is the theory of gravity that explains, or we use to explain, the dynamics of the universe, that scientists, including Einstein, thought that the universe was the Milky Way, that they were the same thing. This, of course, is a somewhat misleading thing. In this picture, you see the bulge of the Milky Way, you see the disk of the Milky Way, you see the obscuring dust of the Milky Way. But the most important thing in the picture is over here. This is another thing called a nebula at that time. We'd call it a galaxy today. And the understanding that the galaxies were distant and separate from the Milky Way didn't come until the next decade, beyond 1915. Well, as I said, Einstein was thinking about how to apply his ideas about gravity, about general relativity, to the universe as a whole. And I just wanted to say that, it's not clear that people's ideas have gotten that much sharper than Einstein's time in 1915, but we know that the instruments are better. So if you look at this picture, which was taken with a photographic plate, you'll see that there's a person behind Einstein who was wagging his head, no, 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 while the shutter was open, and that the person in the chair sitting next to Einstein on his left got up and left while the shutter was open. Our modern technology is better in many ways, and one of them is that we can now see what people were thinking. In this picture, we can now see that Einstein was thinking about the universe. He was thinking it must be static. But you have to remember that what he meant by universe was the Milky Way, and the Milky Way is not expanding or contracting in a systematic way. He knew that he had gravity pulling in, so he added in, by hand, an extra term in his equations that did something like pushing out, and called the cosmological term. People sometimes say Einstein had a kind of religious vision about the eternity and the universe and so on. Well, here's what he said. He said that term is necessary only for the... Can you read this? It's in German. He said that term is necessary only for the purpose of making possible a quasi-static distribution of matter as required by the small velocities of the stars. So he justified it by appealing to the observations that showed that the universe wasn't expanding or contracting, but he meant by universe was the Milky Way. And here he is with the Dutch astronomer De Sitter. He's in De Sitter's space here, and they are looking at this blackboard. And if you look carefully, there's a lambda in there. I'm not sure it's really the same lambda. It could be a Lagrange multiplier. Anyway, he's got something up there that looks like lambda. Now, the progress in astronomy was very fast in 1915. And after the First World War, people began to understand the dimensions of our own Milky Way galaxy. It's interesting that we're not at the center of the Milky Way. People found that out. And in fact, you can see that Pasadena is located far from the center of the Milky Way. Part of the method for doing this was to use variable stars, stars that pulse. And it turns out that the star pulsation gives you a clue to which are the brighter ones and which are the dimmer ones. This demure woman working at the Harvard Observatory, Henrietta Swan-Leavitt, measured a certain kind of star where they were all at the same distance, and she found, as she said here, it's worthy of notice that the brighter variables have the longer periods. Now, the reason that's important is that we have a lot of trouble when you go out at night telling which things are nearby and which things are far away. So if you go out on a spring night in New England, well, summer, you can see fireflies, you can see airplanes, you could see planets, you could see stars, and you could see galaxies. But it's very hard to know which is which. And a trick that astronomers have been using for a long time is to measure the distance to things from their apparent brightness. So if you know how bright something really is, or if you know that it's the same brightness as another object, then you can tell which one's near and which one's far away from the apparent brightness. It's like looking out, at the ocean, and you see boats nearby, and you see boats far away. And the ones nearby, the lights look brighter than they do far away. If you look at a navigation book about this, it says, do not judge the distance to a light from its brightness. The reason is, of course, that fog and other things can affect the way a lighthouse might look to a ship trying to navigate along the coast. The penalty for being wrong in astronomy is, an erratum. You write another paper. In coastwise navigation, it's shipwreck and death. Anyway, You all know that Mount Wilson was, of course, the site of a great technological leap forward. After the First World War, they put into operation this wonderful telescope, the 2.5 meter, well, it used to be 100 inches, now it's 2.5 meters, telescope at Mount Wilson. And again, when you look at the picture, it's a little hard to pick out what is the most important thing in the picture. The most important thing in the picture is, of course, the astronomer who's not there. That's just the chair. But here is Edwin Hubble sitting in that bentwood chair up at the very dangerous Newtonian platform from which, well, you just don't want to be there at night, I'll tell you. It's very dangerous. Nevertheless, what Hubble did, of course, was use the same kinds of stars that Henrietta Leavitt had noticed, and he searched for them in nearby nebulae to find out how far away they were. So here's a picture of the Andromeda galaxy, nebula, he would have called it, in 1923. And you can see that there's a fuzzy patch of stars in the middle, but then there's some individual stars, which he's marked N, those are the novae. And then up at the top with a red circle around it, there's something that was an N, and then he crossed it out, and he put var for variable, because it wasn't a nova that exploded once. It was a variable star that came back again and again and again. And by comparing the period, the time it takes to get bright and dim and bright again for this star with the ones that Henrietta Leavitt had studied, he assumed that they were the same kinds of stars. By noticing that they were maybe 200 times fainter, he figured out that the distance to the M31, to the Andromeda galaxy, was 10 times as far as the distances in the Milky Way. That this was not part of our galaxy, but apart from it. It was a separate system. And Hubble worked quite assiduously measuring the distances to nearby galaxies where he could use this technique to establish their distances. Other things were happening at Mount Wilson too, as you all know. It first had a solar observatory. And one interesting thing is that George Ellery Hale, the man who really propelled the construction of the Mount Wilson and of Palomar, was a real proponent of using the newfangled technique of spectroscopy, taking the light from a star and spreading it out into its constituent colors, because you can find out a lot about stars that way. One thing that you can find out is what they're made of. So the stars are made of atoms, but the atoms are the same as the atoms on the Earth, which you can study in the laboratory. And you can tell what chemical elements are in them. The galaxies are made of stars, so the same thing applies to the spectra of galaxies. So here's a picture of George Hale. You can tell what year it was from the kind of telephone that he was using, I guess. And here is a spectrum of a galaxy. So, you know, an astronomer's job is to take something beautiful, like a rainbow, and turn it into a graph. And so that's shown here. You see the spread out rainbow, and then up above, you can see this jagged graph. The places where the spectrum of the sun or of a galaxy is missing light are the things that really tell you something. This is like a Zen thing, you know. Where it is not there, that's where it is. And you see here that there are lines, these vertical lines, which are places where the light is missing. Those are places where the atoms in the atmospheres of the stars absorb the light. And those spectrum lines are quite interesting. Turns out when you measure them for galaxies, these systems that Hubble was studying, these nebulae as people called them at the time, that they show an interesting property. They are not just standing still. They're coming toward us or going away from us. So here's an image at the Lowell Observatory in Flagstaff. Here's the guy with the interesting name of Vesto Melvin Slifer, observing with an instrument that takes a photograph of a spectrum. And the point is that because there are all those lines whose wavelengths we know in the laboratory, you can tell whether something's coming toward you or away from you. The method for doing that is to see whether the wavelengths are stretched to longer wavelengths or to shorter wavelengths, which is a thing we're used to for sound waves. We all know that when a car goes by at a high rate of speed, you hear it's pitched up as it's coming toward you, and then it lower pitch as it goes by. And of course, if you're in the car, it all stays the same. That's like being in the laboratory. But if you're standing on the side of the road as this thing zooms by, you can tell whether a car is coming toward you or going away from you. But we're not used to seeing that for light, and the reason is that the speed of light is 1,000,000 times the speed of sound. Otherwise, cars that were coming toward you would look a little bit blue, and cars going away from you do look a little bit red, but that is not the reason. That is not the reason. That is not the reason. So it turns out that Hubble had measured distances to galaxies and Slipher had measured the velocities of galaxies through the 1920s. But it wasn't until 1929 that Hubble put those two things together. So in 1925, Hubble had distances and Slipher's had velocities. And why didn't he put 2 and 2 together to kind of see what was going on? Turns out he was inventing a kind of mechanics of psychology. As he says, he had natural inertia. And he said, a natural inertia in the face of revolutionary ideas, couched in the unfamiliar language of general relativity, discouraged immediate investigation. That's from Hubble's book, The Realm of the Nebulae, in 1936. So what he's saying is, some of my students said that they had natural inertia, and that's why they missed the exam. Natural inertia. Anyway, in Hubble's book, it's quite interesting. Every time he uses the passive voice like that, he means me. I did it. Anyway, here's the graph that he didn't make until 1929, and we call it a Hubble diagram. And the vertical axis is the velocity, measured by Slipher in the first instance, but then by Hubble and Humason. And horizontally, the distance, which Hubble inferred from the brightness of variable stars and then from other techniques on the horizontal axis. We call this a Hubble diagram. He called it figure 1. And you can see something here. You can see that as you look at more and more distant galaxies farther out along the horizontal axis, that they have bigger velocities. And the way this plot is made, the bigger velocities are the ones moving away from you. So you'll notice there are just a couple of galaxies moving toward us. M31, the Andromeda galaxy, is one of those. Check your homeowner's insurance. But most of the galaxies are moving away from us. Away from you. This may lead you to the kind of illusion that many of my students, and I believe all members, at least the tenured members of the faculty at my institution have, which is that they personally are at the center of the universe. But if there's any lesson from the history of science, and I'm not sure that there is, but if there's any lesson from the history of science, it's that thinking that we're at the center has been a bad bet for 400 years. Is the Earth at the center of the solar system? No, probably not. Is the sun at the center of our Milky Way galaxy? No, the sun is not at the middle of the Milky Way. It's out in some spiral arm far from the center. It seems like it would be almost a willful kind of misunderstanding for us to say, oh yeah, that's all true, but our galaxy is somehow at the center of the universe. So the question is, how do you reconcile these two things, that you see expansion away from us and the thought that we're not at the center of things? Well, the idea is that if you had a universe that was stretching out in all directions, that to every observer, it would look like the universe was stretching away from them. Let me show you this through the power of animation. And here I've taken a picture and I've just stretched it out a little bit going from frame to frame. What you can see is it looks like all the galaxies are moving away from that one in the middle. What's more, if you look at it kind of carefully, you'll see that the galaxy that was nearby has moved a short distance. The galaxy that's farther away has moved a big distance in the same time. So it's just like Hubble's law. The nearby things are moving away slowly. The distant things are moving away more rapidly. Well, this doesn't prove it, but if you assume that the universe is homogeneous, same everywhere, isotropic, the same in all directions, It turns out that you ought to see something like Hubble's law according to the principles of general relativity. So what about that? It turns out that, although most of the textbooks say at this point, well, Einstein gave up, not quite true. Here you see De Sitter, he's the guy that Einstein was talking to in that crowded little office, depicted in the shape of the Greek letter lambda. Over here on the left is Professor Willem De Sitter, and you can see it was De Sitter's notion and the cartoonist's idea that it's the lambda that's making the ball swell up. English is a dialect of Frisian, you know that. And so you can read Dutch. It says, what makes the ball expand? What makes the universe expand or swell up? That has to be lambda. No other answer can be given. Wow, that was 1930. In 1931, Einstein came to visit Mount Wilson, and here he is. Hubble is keeping a close eye on him. The observatory director looks a little worried. And then here they are, where Einstein's in a more comfortable pose with chalk at the blackboard in the library at 831 Santa Barbara Street. The library looks exactly the same. Well, not exactly. People have changed. But it's a very similar setting. And you can see here, everybody's very proud to have Einstein visiting. Hubble is the tall man there, and George Ellery Hale is patting him on the head for his good work in showing the expansion of the universe. But you remember, Einstein had put this cosmological constant in to make the universe static, to make a balanced universe. So somewhere in the early 1930s, he and De Sitter gave up on the idea that it was lambda doing it. They just stopped talking about lambda. So if you go to the National Academy of Sciences and you go outside to get away from the stuffy atmosphere and you look at Einstein's statue, you can see this bronze tablet, which he brought down from a mountain, and what you won't see on it is any sign of lambda. So I climbed up on the statue to take this picture for you. The park police came pretty soon, so you're lucky I got it. Anyway, at the bottom you see E equals mc squared. That's the only equation people know, mostly. Next equation up is the one for the photoelectric effect. The Nobel Prize Committee was not too clear about this relativity stuff. They said, that's good, we know that, you can have a prize for that. Up on the top line is the basic equation for general relativity, and on the left it tells, on the right it tells what the sources of mass and energy are, and on the left it tells how space is curved as a result, and there's no lambda in there. There are a lot of funny looking symbols, but there is no lambda. So, all right, so Einstein gave up. He said, fine, it's an expanding universe. That lambda, I never liked it very much anyway, so let's get rid of it. But I'm going to tell you tonight is that we need something very similar to that cosmological constant, because the universe is not only expanding, but as John mentioned in the introduction, the expansion is speeding up. And the tool for finding that cosmic acceleration has been supernovae. So I had to read Hubble's Realm of the Nebulae. I had to. When I was a freshman in college, I took a freshman seminar, and one thing we read was Hubble's Realm of the Nebulae. And then 2 years ago, the people at Yale University Press called me and they said, oh, we'd like you to write an introduction. I thought, oh, an introduction to the Realm of the Nebulae. Fabulous. I'll just have to read it again. So it's like reading Great Expectations for the second time. The first time you read it, Pip is kind of young. And then the second time you read it, if you're in college, he's like 4 years older. I thought, how did that happen? In the same way, this book, Realm of the Nebulae, which you might think is about the nebulae and galaxies, turns out it's really about supernovae. And here are the passages that prove it. Here's what Hubble said. Supernovae can be detected at immense distances. And in principle, they are a criterion of distance about as reliable as that of total luminosities of the nebulae. In other words, you can use this trick that he'd been using for measuring distances to galaxies by studying the stars. I show you on the right a galaxy that's got 100 billion stars in it, and then up above is a supernova. That's a star in that galaxy, which for a little while is glowing 4 billion times as bright as the sun. Supernovae can be detected at immense distances. Then, you know, Hubble was one of the first Rhodes Scholars, and so he went from Missouri to the University of Chicago, and from the University of Chicago to Oxford. And when he came back, he spoke with a British accent. It was quite interesting. And you can tell by the way he wrote the book. He says, actually, however, the maxima, that is, the supernovae get bright and dim. Actually, however, the maxima are so seldom observed, and the supernovae themselves are so rare that they contribute very little to the present problem, the problem of measuring cosmic distances. So I'm here to tell you tonight that the advance of technology has made it so we can find lots of these supernovae and exploit them for this purpose over immense distances, and that they work about as, their distance measurements are about as reliable as any that we have. Our knowledge about supernovae comes from Fritz Zwicky and his colleagues, who took up this idea that those explosions in the nebulae must be much more luminous stars, and he wanted to find out what they were. To do that, he needed a camera that could cover a big patch of the sky, and he built the first of the Schmidt telescopes at Palomar. That was the first telescope at Palomar, and the first good-sized Schmidt was the 18-inch Schmidt that he used, and that I used a little bit when I was a graduate student at Caltech. So here's the idea. You have a galaxy of stars, and the stars, generally speaking, last a long time. But every once in a while, there's a star that comes to the end of its life. And a supernova explosion is a star that's dying in an explosive way at the end of its life. And, interestingly enough, for a certain kind of supernova, the thermonuclear supernovae, where there's an exploding white dwarf, the luminosity, the amount of light coming out, is very similar from one to another once you make the appropriate corrections, and that you can use them to make a Hubble diagram. So here's an old one, really, but it's a Hubble diagram for this kind of supernova, and what you can see on the vertical axis is velocity, on the horizontal axis is distance, and this is going out to a distance of about 2 billion light years, which is actually only partway back to the Big Bang. So just to say, the speed of light is a poet's kind of term for really fast. But for astronomers, the speed of light is very slow, and it's what allows us to see what was going on in the past. The speed of light is a foot. That's a unit of distance used in the United States and in Myanmar. A foot in a nanosecond, in a billionth of a second. So when you look out and see the world, you do not see it as it is. You see it as it was. And I'm looking down here, I see people, I see them about 15 nanoseconds ago. Curiously, the people in the back seem younger because I see them as they were 50 nanoseconds ago. Okay, just a joke in the room, but it's not a joke in the astronomical world. When you step out at night and you look at stars nearby, the stars nearby might be 5 or 10 or 100 or maybe even 1,000 light years away. So you can easily see light that was emitted when the Federalists controlled both houses of Congress. And the distances to the galaxies that Hubble established were millions of light years. And so it's not a joke that we really see ancient light. Well, all right. What about these supernovae? This shows that the supernovae lie along the Hubble diagram. That means they can be used to measure these distances. And as I said, this diagram goes out to about 2 billion light years, but we can go farther back than that. Let me say a few words about the supernovae. In the modern day, if you had a supernova, you'd get a message, an email message, or your beeper would go off or something. In the old days, they got out and they made engravings of astronomers rushing out and looking up at this. This is supposed to be Tycho's observatory, Uraniborg, and there up in the constellation Cassiopeia is the supernova of 1572. So that's the other thing to say. Supernovae are rare. Hubble said that. He said that they are so, actually, however, he said they are so rare that they don't contribute much to the problem. We think that a supernova goes off about once in 100 years in a galaxy like ours. We haven't seen one since 1604, but there are lots of parts of the galaxy that are obscured by dust, and they might not have, there could be supernovae that we're not seeing. In any case, if you look now at the place where Tycho measured the position of the supernova of 1572, you see a mission that can be represented this way. This is not anything you could actually see through a telescope. This is an image which is optical light, so you see some stars and a few little wisps of gas around the periphery of this thing. It is a radio image, so it turns out these explosions produce powerful radio emission. And it is an X-ray image. The fluffy stuff in the inside is the X-ray emissions coming from gas of a few million degrees Kelvin. And what's interesting is that with the X-ray emission, you can actually tell what the chemistry is. And it turns out when these stars explode, they make iron. They turn carbon and oxygen into iron, and they get the yield of nuclear fusion that goes all the way up to iron. You might say, well, that's all very, very well, and it happens every 100 years. And so, but this is of real interest, should be of real interest to you. There's iron in your blood, and you might ask, where did you come from? Where did the atoms that are in your body come from? And they came from generations of stars that lived and died before the sun was formed. The sun is a second generation star, later generation star, and it inherited from its forebears the heavy elements that they produced when they died and exploded. So when you look at this object here, you might say, oh, where was that made? You might say, well, I believe that was made in Pontiac, Michigan in 1951. No. I mean, yes, but no. There's 3,200 pounds of iron there that was manufactured in supernova explosions over 5 billion years ago. So this is just a way of saying you're not apart from the universe, you're a part of it, and the things that you see around you came from somewhere, and they came from early generations of stars. Okay, so here's a little bit more about the supernovae. They get bright and they get dim. That's what that just showed you. That was about a month of light images of a supernova. Let me show it to you again because we had to go out there every night and it was cold. There we go. All right. So it gets bright and it gets dim. And we have got, as I was saying, the advance of technology is what has made it possible both to measure the light from the supernovae more precisely and to search widely, searching many galaxies for supernovae. So here's just to illustrate that. Here's my thesis advisor, Bev Oak, and he's a happy guy because he's holding there one of the largest CCDs, chart-coupled devices, the guts of a digital camera, which was 0.24 megapixels. And it takes more to make people happy now. Here's John, but you can see that this guy, even though he's wearing a mask, this is John Tonry, and he's looking at a big hunk of silicon. That big black thing down there is a detector made of silicon that operates as an electronic camera that's as big as the old photographic plates that we used to have. So that's the beginning. It means you can take a picture like this one that has thousands of galaxies in it. Now, I said there was a supernova about every 100 years. A year has about 50 weeks. Okay, don't get excited. It's just an approximate calculation. Or in France, I believe a year has fewer weeks. But anyway, here you see these are galaxies. All these blobs are galaxies. And even the faint little things, the things that look like little grains of sand, they are galaxies, each of which has 100 billion stars. How many galaxies do you have to look at? Well, if it's 1 in 1 in 100 years, that's in 5,000 weeks. So if you looked at 5,000 galaxies, your chances of finding one within a week of maximum would be pretty good. And if you looked at 10,000 galaxies, or 20, your chances of seeing a nice fresh supernova tonight would be very good. So all you need to do is get some really diligent graduate students. And get them to look at 20,000 images every night and see if anything has changed. They won't do it. They won't do it. But what they will do is they will write software. So here's a time travel picture that shows someone who could have been me and Brian Schmidt, who's telling me how easy it's going to be to write this software to find the supernovae given these big digital images. And I said, well, you know, there's this other group, Saul Perlmutter's group at Lawrence Berkeley Lab, and they've had 3 people working on this for 5 years, and, you know, their software is pretty good, and how long do you think it'll take to make yours? And he said, well, about a month. So that turned out to be both true and false. There was software in a month. It didn't work very well, but it got better fast. And here's the idea. Instead of looking at each of the little bits of the picture yourself with your eye, you would do a subtraction. These are digital images. They are numbers in a computer, and you can do that. So here in the middle, I show you a picture. This would be 1/1000th of the image area, and it's got a few blobs in it. Over on the left is a picture which you might think of as taken a month ago. So last month's picture and, let's say, last night's picture. And then, over on the right, is the subtraction of last month from last night. And you can see that if you do this right, all the things that stayed the same, like that fuzzy little spiral down on the lower third of the picture, goes away. And all that's left is something that was not so conspicuous when you were looking at the image itself, but it's very clear when you look at it in the difference image. And not only that, it has a red circle around it, so you know this must be the right thing. So that's the beginning, having these big electronic detectors and having the software to run through lots and lots of galaxies to find the supernovae. That was one part of the problem which technology solved. There is, however, the problem of dust. I said we're judging the distance by the apparent brightness, and I said it's not so good for navigation and so on, but there is an analogous problem for us, which is dust. Every household has dust, and it turns out the Milky Way has quite a lot of dust, and so do the other galaxies, some of the other galaxies. So you don't know for sure when you're looking at a supernova whether you're seeing its full brightness or you're seeing it dimmed a little bit by the absorption by dust. And if you think about it, a supernova that's dimmed by dust, you will mistake it for being farther away than it really is, because you'll think it's dimmer. If you think the dimness is due to distance, it'll be a bigger distance. But if it's due to dust, you'll be wrong. So you have to figure out some way to accommodate this idea that the galaxies, including ours, have some dust. So I had another graduate student. I said, that would be a good project for you. So here's Adam Rees, and here's the day he got his PhD. I'm wearing all the answers to the final exam on that vest. So this is in the early 1990s, and as I mentioned, there was another group in the field. Here's Brian Schmidt and Saul Perlmutter discussing the work of each team. I think Brian has him outweighed, and we're outclassed, we say. And it turns out in 1997 or so, we began to get some results. Here's a page from Adam's notebook. Adam went to MIT, and at MIT, they teach you to keep everything in a notebook. So here's a page from his notebook, and there's a lot of writing there, but there's a big fat arrow pointing to the place where it says something about what fraction of the universe is in the form of gravitating matter, and he has minus 0.36. Minus? He called me up that day. He said, I got this answer, and it's minus 0.36. I said, well, you must have done something wrong. You must have left out the square root of pi or something like that. But it turned out that's not so, that we checked this carefully and found that the universe was acting as if it had negative matter, as if it had something that made the universe speed up, as if it had something just like the cosmological constant, which we had learned never to think about again. So here's the data. I showed you Hubble's Hubble diagram, and it was kind of scrawny and didn't have too many points. This is sort of the equivalent thing. Up at the top is the Hubble diagram part, but down at the bottom you can see where we've subtracted out that 45 degrees. And The idea is the dashed line around the bottom is what you'd get if the universe was slowing down, which most people was betting, or many people were betting that would be true. The horizontal line is if the universe is slowing down just a little, but even without the powerful tools of Bayesian inference, you can see that the points lie up a little bit, and the line that goes through those points over on the right-hand side is a universe that is accelerating, as if it had a cosmological constant or something that acts very much like it at work. The points here are from our team and from the other team. We have fewer points, but smaller scatter, I may say. And the two teams put out their results in this kind of form, where these big ellipses tell you how probable is it that there's a certain amount of dark energy and dark matter in the universe. So the idea is that there's some matter that is gravitating and trying to slow things down. There's this other stuff, which might be the cosmological constant, trying to speed things up. In 1990, if you punched a theorist in the shoulder and said, where do you think it's going to be on this diagram? They would say, there, well outside the region that we found. If you punched me in the shoulder in 1990, or any observational astronomer, they probably would have said, well, probably here. It looks like the density is maybe 3/10 of the density that's needed to make the universe bound. And that was the observational part. But what this is saying is you don't want to be on that line, you're not on that line with zero dark energy, that the real data is pushing you up into this strange, unfamiliar territory in which you need something very much like the cosmological constant. This made Einstein very happy. Well, surprised, I guess. Anyway, sort of surprised. And not only that, it led him to start writing. He's carrying a sheaf of paper under his arms. You can't see it very well, but the top sheet says lambda on it. It's interesting because, of course, he's been dead for some decades. But anyway, this is what we imagine he might have thought. So here's the idea. We have a universe which has both dark matter and dark energy, and there's a kind of tug of war going on in which the dark matter is trying to slow things down. The dark energy is trying to speed things up. And as time goes by, it turns out, the density of matter will go down, but the accelerating part, if it's the cosmological constant, will stay the same. So eventually, the accelerating part will win if there's a tug of war between dark energy and dark matter. So we think that's the kind of universe we're in. It means that in the future, the universe will be expanding exponentially. That is, the speed will get bigger, proportional to how big the universe is. Well, what have we been doing since 1998? Well, we've been filling in that diagram. So here I show you a diagram that shows redshift across the horizontal axis and distance on the vertical axis, just to fool you, because we did it the other way before. And it's log, and it's a very highly professional diagram. But in any case, what are the implications? This is the thing I showed you before that shows how much dark matter and how much dark energy. And what the data show now is that this is really right. That, you know, this result, which was a little marginal in 1998 and 99, really seems to be true, and that the universe really is accelerating due to some kind of springy stuff that makes up most of the matter and energy in the universe. So you could say we discovered most of the universe just 20 years ago. Now, you can do this yourself. Well, you can't discover it because that's been done. But anyway, you can make this judgment yourself. And so what I've done here is I've drawn those points represent the relation between redshift and distance for the supernovae, binned up nicely. And then the thing that's changing, the line, is what you'd expect if different fractions of the universe were in the form of the dark energy. And you can see if it's all dark energy, well, that doesn't fit, or if it's no dark energy, that doesn't fit. But somewhere in there looks pretty good. And that's about 2/3 or 3/4 of the universe in the form of this springy stuff, this dark energy. Well, here is, of course, a great leader in astronomical research, Galileo, and he's showing people his telescope out in front of the Doge's palace there in Venice. And Galileo said, all truths are easy to understand once they are discovered. The point is to discover them. So that's a good way to think of it. So I'm sorry, although you did measure the dark energy, you were not the first. Here's the way this seems to play out. That we have a universe which is only 4% atoms of the regular type, the type that you and I are made of. Turns out the gravitating stuff we think is probably not made of neutrons and protons, but something else, which we haven't identified, called the cold dark matter. And that the dark energy makes up the balance of this. Now, my theoretical friends are very proud of this. They say, look, the diagram is full. I only ask you to ask, what is it full of? And in this case, it's full of our most important resource, which is ignorance. That we don't know what the dark matter is, and we don't know what the dark energy is. So I think this is a good thing. I think this means there's plenty more for us to do, and the youngest people in the room are the ones who may be the ones to sort this out. Nevertheless, you know, it's time to ask, how does this make you feel? I've got to say, just living in that little slice of the pie, 4%, you've got to realize that all pie is actually made of baryon, you know, the particles that are in that 4%. We're made of the 4%. Makes me feel special. What about the dark energy? Well, in the old days, before you could Google, now when you Google dark energy, you get self-congratulatory explanations from various august institutions about how they discovered it, or they'll make it better, or something. But in the old days, you would get this from American Hydroponics in Berkeley, California, a manufacturer of plant food for growing controlled substances in your closet. And it referred to the chemical processes. It said those specialized processes are also responsible for the very distinct odor of dark energy. So we don't know what it is, but we know it smells bad. What about this picture of a universe in which the things you see, the stars and the galaxies, are just tracing a battle, a tug of war between the dark matter and the dark energy, which you don't see at all? How do you put your mind around this problem? Well, you know, again, metaphors may help. Here you see a mountain. You do not see the mountain, grasshopper. You see the snow. You see the snow, which would be like seeing the stars in galaxies and the galaxies. The thing you don't see is the thing that gives the mass to the mountain, gives the presence of the mountain, and that would be like the dark matter. The mass is the mountain. Or, well, all right, you might say, well, what about the dark energy? If you go onto the internet and you look up dark energy, people will say things like, scientists don't know what it is. Well, yes, of course, that's true. We're just being modest. We don't know for sure what it is. But it isn't as though we have no idea that it's there. Dark energy is something whose presence you detect from its effects. And this is not, you don't see the dark energy, but you see what it does. It makes the universe expand faster. And this is not so unfamiliar an argument. If you look outside and you see the trees moving back and forth, and you ask somebody, hey, what's making the trees move back and forth? They'll say, it's the wind. You don't see the wind. You see the effects of the wind. And so in the same way, we see the effects of dark energy. Okay. What about the future? Are we going to harness dark energy to make flying cars? No. But let me say a few things about what kind of investigation we will have about the dark energy. One is, I said, you know, there's a physical theory, and theorists know that if you look on very small scales, you're uncertain about what the energy might be for, let's say, electromagnetism. Particles and their antiparticles can jump out of the vacuum, and virtual particles can be formed and annihilate. all the time, and the world really acts like that, not like a world in which the vacuum has no properties. For this, the energy in the vacuum associated with gravity, you can also make an estimate, but it turns out to be one of the least accurate estimates in the history of science, I believe. If you ask, is the dark energy the cosmological constant? You get the envelope shown here, and you do it on the back of an envelope. You find something that's related to the scale of gravity. And it turns out it's about, the number you get is about 10 to the 120 in units where the observed value is 0.7. This is what in academia we call not good quantitative agreement. It's what other people call wrong. There's something wrong here. Why is the energy associated with the vacuum so small? We don't know. Is the dark energy the cosmological constant? Or could it be something else that acts sort of like the cosmological constant? And we are going to find out. I turn out to be licensed to work in this field. I have a union card from the International Brotherhood of Theorists. I'm a member in good standing, and those of you with good eyesight will see that it's valid to infinity. Okay? And so we're going to take a look at this problem. It does bother some people, though, that it doesn't seem to make sense. It's not a common sense universe. All I can say is your common sense comes from playing baseball, and the balls go up and they come back down. This is like a situation where you throw a ball up and it takes off and flies away faster and faster. Anyway, I had an experience where this was brought to me in a pithy way when I saw a T-shirt that had a slogan embodying this idea on it. And interestingly enough, the quotation is from me. And I had no idea that these T-shirts were being manufactured. It said, although the universe is under no obligation to make sense, your PhD thesis ought to. Okay. I am improving it. Okay. So one way to think about the dark energy is as a kind of property of space that ought to be put back into Einstein's equations. And so I was trying to do that the last time I was in Washington. And again, as I mentioned, the park police interfered with that improvement in those equations. Now, I said at the beginning I wasn't going to give credit to anybody, but that's not true. The investigation of the properties of the dark energy are being carried out by lots of people, including a very good group here at the Carnegie Observatories that are studying supernovae. There's Mark Phillips on the left, who's someone who's really improved the data and helped us understand better, especially for the nearby supernovae, what's going on, and especially by making the measurements out in the infrared. And I've been following that up a little bit. Here's a supernova on the left, detected on the ground. So the thing with the blue tick marks on it is the supernova. The fuzzy thing to its left is a galaxy, done in the kind of way I showed you before. But in this case, we've been using the Hubble Space Telescope to observe that supernova at infrared wavelengths, where it turns out the dust is less of a problem and the supernovae behave better. And so you can see that blue arrow is pointing to the same thing. There's the fuzzy thing, which is the galaxy, and that nice hard dot, which is the image as seen with the Hubble Space Telescope. This idea of going into the infrared is something which is going to be very important in astronomy in the coming years. Here is a picture of the James Webb Space Telescope, which is going to be the successor to the Hubble Space Telescope. 6.5 meters, cold telescope in space. It has to unfold in space. It's quite a terrifying thought. And it is going to be launched in 2018, so that's not so far off. And of course, here in Pasadena, is the home of the giant Magellan Telescope Observatory, where people are working now to design and build this wonderful telescope that Carnegie and Harvard are partners in with many other organizations. And we're working on building this thing. We're making some pretty good progress. For example, we've been able to level the mountain in Chile, where this is going to go. And we've been making the mirrors. Maybe you saw there are 7 big mirrors there. Those are 8 meters across, so as big as this stage, and each one of them. arranged in that pattern that you see. And we've made one of them. The first mirror has been polished to what I would say perfection. The second and the third mirrors have been cast. And we had such a good party at the last mirror casting that we made one of them out of ice. And whoops. And so here's a mirror made of ice. So you can, it's not full scale, so you can see what's going on. There's nothing funnier than ice in Tucson, I gotta tell you. And what has this got to do with type 1 supernovae and the dark energy? Well, one of the things we'll be able to do with this giant Magellan Telescope is to get images which are 10 times sharper than the ones that you get with the Hubble Space Telescope. So that's illustrated here. The panels on the left shows a galaxy, on the right shows a galaxy with a supernova as observed by the Hubble Space Telescope. There's another one down here. The red one is a spiral galaxy, and on the right is a spiral galaxy with a supernova in it. And just to give you a feel for this, the size, the blurring of the images that is caused by the Earth's atmosphere at a good site like Las Campanas is about the size of that big circle up at the top. The Space Telescope makes images represented by that second image, and you can see that that compares fairly well. This is sort of honest. It compares pretty well with the images we actually have. But with adaptive optics, the ability to take the wiggles of the atmosphere out, and a big telescope like the giant Magellan Telescope, we'll have images in which the images of a point source, like a supernova, will be that little tiny dot. And that makes it a lot easier to measure the properties of the supernovae at great distances. Okay, well, that's maybe enough. I promised you I would show you the cover of the best book I know on this subject. It's called The Extravagant Universe, Exploding Stars, Dark Energy, and the Accelerating Cosmos. And yes, it's still in print. And then I just wanted to say one more thing. When I was president of the American Astronomical Society, sometimes I was called upon to speak up for science. And I did my best, but you know, there were other people, the physicists, the chemists, and a bunch of other people also speaking up. And they would make arguments that, you know, they're all right, but they didn't sound quite right to me. They would talk about science for technology, that as an economic engine, technological development is certainly important. They'd talk about defense. Certainly, it's a dangerous world. You don't want to have an inferior defense. And a lot of the congressmen are kind of old people, and so medicine is always something that they're interested in. And I think all these things are good things. I'm not against any of them. I would like to be rich and safe and immortal. Well, if not immortal, just very long-lived. But I don't think this is the whole story, and I don't think that's why we do this kind of science. Because I don't think it would be a perfect world if you were rich, safe, immortal, and bored. And we are curious people. We want to know where we came from. We want to know where we're going. And astronomy addresses those big questions in a very direct way. So this kind of work, I would say, is science for the joy of finding out how the world works. Thank you very much.
Questions? Uh-oh. There you go. Stand by. You're it. You. That's you.
So, lambda represents the I can't say that. Constant, right? So, does that mean that it actually means that, or does it mean something else?
Well, that's just the Greek letter we use for this idea. And the idea is an energy that's associated with empty space itself. So it has a very strange property that as the space expands, the amount of energy in it gets bigger. You would think it would get diluted. You know, if you have a paint gun, you should not use this without goggles. But you have a paint gun that there's air in it, and when the air expands, it pushes on something and makes the ball go fast. The dark energy is sort of the opposite way around. You'd have to pull on it as you make it bigger. But it would have this interesting property that if you put that stuff into Einstein's equations and ask what does it do, it makes the universe expand faster over time. So we think it's a property of the vacuum, an energy associated with the vacuum, or it could be something else. It could be some other kind of aspect of the vacuum that is not exactly the cosmological constant. Oh, notice my hands were moving a lot? That's always a bad sign. Somebody doesn't really know the answer, their hands move a lot. Yeah. Go ahead.
Going off of that, couldn't it have something to do with inflation?
Couldn't it have something to do with inflation? Yes, inflation is an exponential expansion due to some other. The idea is that the universe might have done something like this before, exponential expansion for 40 cycles or whatever it takes, so that the initial fluctuations in the Big Bang became the fluctuations in the universe that we see today with the microwave background. And is something where the mechanics of it, or the equations that describe it, are very similar, where there is something, the inflaton, where there's some energy that doesn't decline with time or declines slowly, and so the universe expands exponentially in that early time. So yes, it could be that this is the second time the universe has had exponential expansion. It only began, this current episode, about 5 billion years ago, whereas that early episode was at 10 to the minus 35 seconds. So they're separated by a huge gap in sort of the scale of time and energy. But it could be the same kind of thing or something that's related. So it's a very good question.
Could you say that the cosmological constant ain't constant? I mean, that's...
No, the cosmological constant could be constant, really constant. And the thing that changes is the density in the universe. So as the universe expands, the density goes down. If you look into the past, the density would have been higher. So for a constant cosmological constant, if you go into the past, the universe should have been slowing down due to the higher density. And as you go into the future, the universe will expand faster and faster due to the fact that the matter is getting more dilute, whereas the constant is staying constant. And we have seen that far back. We've seen far enough back to this time when the universe was decelerating. So, which was only a little more than 5 billion years ago, about the time when the sun formed. Yes?
If the universe keeps accelerating and accelerating, is it ever going to stop and then implode, or just keep on going?
It's scary, isn't it? Yes. So that's an interesting question. If the universe is, expanding exponentially, kind of what then? We do not know enough about the dark energy to say for sure that it is the cosmological constant, in which case we can predict what it will do. Then it will be literally exponential, faster and faster. But if the dark energy has some additional properties, which we're just not sensitive enough to measure yet, there's still room for a kind of dark energy that could produce a contraction at some distant time, and a kind of a hot, dense universe again. Or it could be that the expansion will go faster than exponential, and that's not so good. If the universe expands faster than exponentially, you can have eventually a time where the galaxies will be ripped apart, the stars will be ripped apart, atoms will be ripped apart, what we call the Big Rip.
As opposed to the Big Bang.
As opposed to the Big Bang. We get to make up the names. And so I would say our knowledge, this is something we just started to learn about in 1998. And so you can't expect us to have all the answers just yet. But we're working on it. And the kinds of measurements that I was describing, building up the samples, measuring in the infrared, combining with other kinds of data from microwave background and from galaxy clustering, all of those things will help us understand the nature of the dark energy and to be able to say more clearly what will happen in the future. But, you know, we can see, telescopes let us see the past. They're a real-time machine that way, but they don't let us see the future. You know, the future will depend on our knowledge of the properties of dark energy that we are able to extract from the measurements we can make. Yes?
Well, you've been talking about dark energy law, and as far as I know, the only way you can interact with this stuff is by the gravity it makes.
Right.
So if that's the only connection to the world, and that seems pretty slim, could we ever manipulate it? Or could we ever use it in some way to enhance our lives?
Yes, so the question is, can we make anti-gravity boots? No, with this stuff. So it's really interesting. I think what you say is very interesting. The only information we have about the dark energy so far is from astronomical measurements, like the ones I was describing this evening. You would like it to have a laboratory experiment so that you could find out more about the properties of the dark energy, but gravity is so weak that's very hard to do. The situation is not that different than the situation in the 1600s when the astronomers knew for sure that the speed of light was not infinite. It took time for light to get from Jupiter to here and across the solar system, and the astronomers had a pretty good estimate of how fast that was. But it wasn't until well into the 1800s that it was possible to make a laboratory experiment to measure the speed of light, because the speed of light is a foot in a nanosecond. And they didn't have, you know, a pendulum clock does not measure nanoseconds very well. And it wasn't until people got quite clever about measuring a small fraction of a second that there was a laboratory experiment that could measure the properties of the speed of light. And we're in sort of a similar situation here where the effect is too subtle for our instruments and even our ideas at the moment. But that doesn't mean it will always be. And you know, it will be interesting to see if somebody, probably somebody of your age, comes up with a good idea about how to make that measurement. Of your age now, I mean. Yeah. Yes?
Currently, we're able to see all the way back to close to the Big Bang, when the universe went opaque, 300,000 years old, whatever. And that boundary is being expanded further out. Eventually, the universe will be expanding, this is dark energy, exponential expansion is true, will be expanding faster than the speed of light, but you'll no longer be able to see out there and only be able to see relatively closer. What does that have? What implications does that have for what we'll be able to observe?
Right. So the point is, if the universe is expanding faster and faster over time, then the piece of the universe that we can see, because we're receiving light from it, will be a smaller and smaller fraction of the universe as time goes by. That's basically right. Well, I think it means that now is the moment for funding astronomy. You can't, well, we're not going to be able to do this. 10 billion years into the future, it's going to be harder and harder. And then if you look, if you think 10 billion years, of course, we don't know if it's really true, but Andromeda is headed toward us, and so it's not going to escape. And Andromeda will actually merge with the Milky Way galaxy. And then you could imagine a world in which the rest of the universe was inaccessible to us. And we'd just be all alone. And it would be just like that picture I showed you from 1915, when there was just one big galaxy and we called it the universe. So that's as far as I've gotten with this idea. Yeah?
Does the acceleration imply the non-conservation of energy?
Now, that's an interesting question. Does the acceleration imply that energy is not conserved? Gravitational energy is negative, so it turns out as you expand this thing up, the energy can stay constant. So, you notice that? See that? Energy can stay constant, yeah. But you don't have to conserve. I mean, you don't. That's a hard question, but next question. Hey, I'll go over to this side of the room. What's this deal here?
We'll take you that you have a couple more.
All right, yes. They're getting tough now.
Yeah.
Since the dark energy kicked in about 5 billion years ago from some unknown power source or whatever, what are the odds that 2 billion years from now it'll kick out?
Yeah.
So the question is, I'll repeat that slowly so I can think. So the point is that the dark energy seems to have taken over about 5 billion years ago, and how do you know it won't stop at some time in the future? Well, we surely don't know for sure. This business of, if it's the cosmological constant, which is the simplest thing, then we can say what it will do, and as you go into the past, you should see this deceleration. You know, the change from deceleration to acceleration. Everybody knows that a change in position is called velocity. A change in velocity is called acceleration. And to the undying amusement of all undergraduates, the change in acceleration is called the jerk. And so the cosmic jerk sounds like a Jerry Lewis movie, took place about 5 billion years ago. So our knowledge of the dark energy is just not sufficient to tell us whether it will just be a constant or do something else. I guess that's why I think it's so interesting to investigate this mystery and to see if there's any clue that the dark energy deviates from being the cosmological constant. So that's what I'm trying to do with these supernovae measured in the infrared.
Let's see, this woman's had her hand up forever.
Okay.
What is the dark energy expanding into?
What is the dark energy expanding into? Well, you know, I showed you that cartoon there at the beginning that was a bunch of galaxies, and I said, well, the picture's just getting bigger. So that the expansion that you measure is something you can measure more or less locally. You know, if I had the power to make this room twice as big, then the person next to you would end up 2 seats away. The person who was 2 seats away would end up 4 seats. And you would see everybody moving away from you. But that doesn't mean there's an edge, okay? You could have a universe in which was infinite, or you could have one that was closed like the surface of a sphere, where the expansion would be something that you would measure locally. You'd see that the nearby galaxies are moving away from you, the more distant ones moving away faster. But there doesn't have to be an edge in order to have expansion. It seems like a kind of a crazy idea, but you notice I did not have to wave my hands that much because I'm really confident about this one. Whoa.
Is there any association discovered now between the dark matter and the dark energy?
Yeah, so that's an interesting question. The dark matter we know is there because of its gravitational tug on stars that, say, orbiting in galaxies. That's an important thing. The dark energy we see from its effect on cosmological expansion on the big scale. But could they have some relation to one another? Well, the honest answer is we don't know. The only aspect of the dark matter that we really know about is its gravitational tug. But whether it interacts with itself or whether it can decay or any of these other things which are not impossible, we don't know. So I would say for the dark matter, though, since that's the question, people think that it might well be a subatomic particle that has mass but no electric charge and only interacts by the weak force. Now, you know of a particle like that. It's called the neutrino, but the mass for the neutrino is too small. So that's too bad that we have a universe with so many parts, and it's like building a kit and you have parts left. Anyway, left over. What are those? Why do we have that neutrino? Why do we have 3 kinds? We don't know. People are looking for this. If there is dark matter dominating our galaxy, then it ought to be in this room. About 1 particle in every liter. And we're moving. We're not stationary. We're moving in our galaxy around the center. We're going at more than 200 kilometers a second. So it's like driving through mist. You ought to get particles bumping into the windshield. So people are looking for that. They've built detectors which are underground to get away from the cosmic rays. Very sensitive detectors that are intended to detect the ping that you get when one of these dark matter particles bumps into a nucleus.
Are these huge tanks of water?
No, those are the neutrino detectors are the big tanks of water. These here you want the nuclei, and so they are hockey pucks of germanium and or jugs of liquid xenon. Turns out that's one of the latest ways to do it. So all of those experimenters are very optimistic that they are going to find this thing, like next year or the year after or the year after that. Anyway, now they've been saying that for 30 years, so.
What keeps you going?
But it does keep you going, and I think, the sense that unless we're kind of completely mistaken and we've got the wrong idea about the dark matter, I think there's a pretty good chance that in the next 5 or 10 years, people really will have a direct detection of it, and that would be very interesting. Okay, I'm worn out.